All right, guys, the last part of our trig graphing extravaganza, sections 5.3 and 5.4, we want to introduce you to the graphs of the reciprocal trig functions. We will not be assessing you on these graphs. For that reason, we're not going to go through any examples where we have transformations like a period change or an amplitude change or so on and so forth. But if needed, down the road, those transformations would work the same as any of our three main trig functions, sine, cosine, or tangent. As long as we remember the general shape of the cosecant, secant, and cotangent graph, we should be able to make those adjustments. But for the purpose of our notes today, it will only be the parent functions of that. And one of the reasons we're doing that is to get you guys to make connections between the graph of a function and then the graph of the reciprocal of that function. So, a reminder that cosecant is the reciprocal of the sine graph. So let's think about what the parent function for sine looks like. So let's draw that out here real quick. Remember, these values basically come straight off of your unit circle, where we think about one cycle of the sine graph. Up to 1 down to -1 starts at 0, pi over 2 pi, 3 pi over 2, and 2 pi. So really why we're doing this in a remote learning environment is that we want you guys to see some connections here between this graph and then the cosecant graph. Okay? Now, based on the reciprocals, we're going to be using... There's no reason to change the 5 parent functions, or sorry, the 5 parent x values, or the 3 parent y values, okay? A cosecant, if a sine graph makes one full cycle in a distance of 2 pi, then its reciprocal should do that as well, okay? If a sine graph has important points if we're going to graph 5 points, the zeros, the ones, and the negative ones, we should still do that with our cosecant graph. So let's start with maybe the easiest of all of these things. Okay, at pi over 2, so at x equals pi over 2, sine of x equals 1. All right. If cosecant of x is the reciprocal of sine, then at x equals pi over 2, the cosecant value should be the reciprocal of the sine value. What's the reciprocal of 1? Well, lucky for us, it is also 1. Okay? So just like the sine graph, we will have a point at 1. And in fact, anytime a function has a point at y equals 1, its reciprocal function will also have a point at y equals 1. No matter what function, no matter what it looks like, that would make a lot of sense because we know what the word reciprocal means. For the same reason, at x equals 3 pi over 2, sine of x is 1, sorry, -1. Let's restate this one more time. If sine of x has a value of -1 at 3 pi over 2, and cosecant is the reciprocal of sine, then cosecant should be -1 at 3 pi over 2 as well. And that will work for every type of function and reciprocal function that ever exists. Okay. All right. Now, what happens at the zeros? Okay. So let's write it over here, at x equals 0, x equals pi, and x equals 2 pi, sine of x is 0. Well, if cosecant, again, is the reciprocal of sine, 0 over any number is 0. That would mean we'd have some number over 0 for the cosecant, because that's a reciprocal of sine. We know that we can't divide by 0 in math. And hopefully you also know that when there is an undefined x value in a domain, that leads to a vertical asymptote on a graph. So the graphical representation of an undefined point is a vertical asymptote, which means the sine graph at every y equals 0 point on a sine graph, we will have a vertical asymptote on its reciprocal graph, or cosecant. Now here's one of the more fun things we get to talk about, okay? What is going to be happening from this point? Okay, what's going to be happening here? This is a wave. So yeah, it's easy for us to figure out that the reciprocal of 1 is 1. The reciprocal of -1 is -1. The reciprocal of 0 is undefined. Let's put some asymptotes. But what's happening here? So let's think of the regular function. As we're getting closer and closer and closer to 0, so let's think of it from this point backwards. As a y value gets closer and closer and closer to 0, the reciprocal of that, so this might be 1/2 and 1/4 and 1/8 and 1/32 and 1/64, and it'll get as close as infinitely close to 0, and that denominator will keep growing, 1/100th, 1/1000, 1/10,000. If you take the reciprocal of all of those, we get 2 and 3 and 4 and 10 and 100 and 1,000 and 10,000, all the way to positive infinity, since we're working on the positive side of the x-axis. So the reciprocal of this piece of the sine graph will go off to infinity. Makes a lot of sense because we have a vertical asymptote there. And vertical asymptotes basically lead us to approaching infinity. Over here, from pi over 2 to pi, again we're getting infinitely close to 0, meaning the reciprocal will be approaching infinity. On the right side, between pi and 2 pi, the same thing's happening. We're getting infinitely close to 0, but on the negative side of the x-axis, where y's are negative. For that reason, that would be the parent cosecant function. Okay? A lot of students like kind of taking a dashed line and drawing the sine curve, and hopefully that will kind of help you piece this together as well. This is the sine curve. Here's what the reciprocal of that sine curve looks like. Asymptotes at the zeros, 1, 1, -1, -1, and then approaching infinity that way. All right, very cool. One more. We'll kind of write the domain here of this one. We won't talk much about the domain and range, okay? But the domain of this cosecant graph, remember, we have a cyclical function with asymptotes. So x will be an element of all the real numbers such that x cannot equal. Pick any of our asymptotes. I'll pick 0. Add the distance between the asymptotes, which this case would be pi, k, where k is an integer. That would be the domain. That gives us just a little more practice on writing the domain of a cyclical function with asymptotes. The range of the cosecant graph, -infinity all the way to -1. And union 1 to positive infinity. No amplitude because this is not a wave-like function. And the period of the cosecant graph would always match the period of the sine graph, which would be 2 pi. Okay? Let's quickly go through the secant graph. Secant is the reciprocal of cosine. From 0 to 2 pi with equal intervals in between. That's what the cosine graph looks like. Just like we did with the sine and the cosecant, let's take a look at how the reciprocal would be. So again, 0, we've got 1, we've got -1, we have our 5 x values. No reason to change them from the x values of our parent function. This will still give us one cycle. Okay? At the y equals 1 points, we will still have y equals 1. At the y equals -1 points, we will still have y equals -1. At the zeros of cosine, we should have asymptotes for secant. Same reason we talked about on the previous graph. As we go from 0 to pi over 2, we're getting infinitely close to 0 on the positive side, which means the reciprocal would be getting infinitely close to infinity. Between pi over 2 and 3 pi over 2, we're getting infinitely close to 0, but on the negative side, meaning we'd be getting infinitely close to negative infinity. For the reciprocal, this piece looks exactly like this piece, same reason. That is the secant graph. We could write the domain very easily. X is an element of all real numbers such that x cannot equal pi over 2 plus pi k, where k is an integer. And secant and cosecant would have the same range, negative infinity to -1, 1 to infinity. Feel free to write that down if you'd like. And last but not least, cotangent is the reciprocal of tangent. Here is how tangent looks. Okay. Now let's think about how the cotangent graph would look. All right. Where tangent is 0, cotangent would have a vertical asymptote. Where tangent equals 1, cotangent would still equal 1. Where tangent equals -1, cotangent would still equal -1. Okay? Where tangent has an asymptote, cotangent would be 0. There we go. I'm hoping after this set of notes, you really get an understanding. I should be able to, your pre-calc advanced teacher should be able to, give you the graph of any function that ever existed, and you should be able to take the properties of that graph, where points are 0, where points are 1, where points are approaching 0, from positive, from negative, where there are asymptotes possibly, or maybe there are no asymptotes. Okay, and link those properties to the properties of what its reciprocal function would look like. And the first time we get a look at that in math, and this comes up more probably in higher level mathematics, but for us, our trig functions, the relationship between the graph of a function like sine and the graph of its reciprocal function like cosecant. All right, so hopefully that sunk in for you guys. You get a nice understanding of those properties and how they relate from a function to its reciprocal.